Let's go. So this is the third lesson of topological data analysis, and this will be the last theoretical lesson of the week. We will talk today about homotopies. So yesterday, I introduced homomorphisms and the homomorphism equivalence. So we learned how to classify topological spaces into homomorphism equivalence classes. Today, I would like to introduce a new equivalence that we use every day as topologists, which is called homotopy equivalence. And the homotopy equivalence is a weaker equivalence than homomorphism. So for instance, we will see that the square, the circle, and the triangle are homotopic, but a lot more of topological spaces also are homotopic to them. For instance, the letter A, or a fat circle, or a square with some dots on it. So let's go. I will define first the homotopy equivalence between maps. Then we will be able to define homotopy equivalence between topological spaces. And I'd like at the end to talk a bit about invariance, as we did yesterday. So let's start with the notion of homotopy equivalence between maps. I need two topological spaces, X and Y, endowed with topologies T and U, and two maps, F and G, from X to Y, two continuous maps. I define a homotopy between F and G as a map F, like that, big F, from X times the interval 0, 1. I take the product of X and 0, 1 onto Y, such that I have three conditions. F dot 0 is equal to F. When I say F dot 0, it means that the second argument of the function is fixed and equal to 0. So if I fix 0 here, I obtain a map from X to Y. And I want this map to be equal to F. When I fix the second argument to 1, I obtain F dot 1, and I want this map to be equal to G. And moreover, I want that the whole map, big F, is continuous. All right? If we have a homotopy, like that, between F and G, we say that the maps F and G are homotopic. So to be really clear, the map F takes as an input two coordinates, a point in X and a point in 0, 1. And when I say F dot T, I obtain a map between X and Y, defined like that. And Guillerme says, so we want to take F and deform it to G continuously. Yeah, this is exactly this idea. Let me give you an example. I consider two maps, F and G, between R and R. The first map F is the constant map equal to 0, and the second map G is this map here. Okay. When I say again that they are continuous, it means that they are continuous with respect to the Euclidean topology on R. And this here I drew a homotopy between F and G. So for every T that you can choose between 0 and 1, you obtain a new function, F dot T. And so, as you can see, a homotopy is exactly a deformation, a continuous deformation between my two maps. Okay, I give here some example of values of t, 0.2, 0.5, 0.6, but it is defined for every t between 0 and 1. A second example, a homotopy between two maps that are defined from 0, 1 to R2. So you can draw a map from 0, 1 to R2 like that. I start with the value 0, and then I draw the function. Okay. So a homotopy between f drawn here and g drawn here will be a continuous deformation between f and g. Okay. Let's take a formal example. I consider as topological spaces x equal to y equal to the interval -1, 1. Okay? And I define the functions f and g as f constant map equal to 0 and g identity. I want to prove that they are homotopic. So if I want to do so, I have to find a homotopy between them. I have to find a map. I extend the first space x with the interval 0, 1, and can do something like that. To every point in x times 0, 1, I define big F of xt to be t times x. So do you agree that if I take t equals to 0, I obtain 0 at the end for every x? So f dot 0 is a constant map equal to 0. This is f. And if I take t equals to 1, I obtain just x, 1 times x. So f dot 1 is equal to the identity, which is g. Okay. And this map f is continuous. So this is an homotopy between f and g. And you can say that f and g, defined like that, are homotopic. And this is an illustration of it. F dot 0, this is constant equal to 0. F dot 1, this is the identity. And in between, I have the linear maps, t times x. For instance, this is the map that maps x to 0.2 times x. Okay. Another example. I define a map here from the circle times the interval 0, 1 to R2, and it's defined like that. If you take theta in the circle, you map to cos theta plus t and sinus theta plus t. Okay. I precise that the notation here, S1, is the circle. So what do we have? If I pick t equals to 0, f dot 0 is this map. You obtain the unit circle of R2. And if you take t equals to 1, you get this map, G. So it is the circle translated by the vector 1, 1. And as you can see, for each value of t, we obtain a translation of the circle. All right, this is a deformation of our circle. Of course, f is continuous, and so this is a homotopy between f and g. So these two maps, f and g, are homotopic. A counter example here. Sometimes you cannot translate your object in your codomain. For instance, if I consider the space R2 minus the origin, R2 minus the point 0, 0, then I cannot find a homotopy between F and G as before. Because if you wanted to translate the circle to the other one, you would have to go through the origin. But the origin is not a point of our topological space Y. We removed the origin. So what I say here is that the homotopy we defined just before is not a homotopy in this example. It is not well defined. And though this does not mean that we cannot find any homotopy between F and G. Maybe there is a way to deform the circle and escape from this problem of the origin. But it turns out that this is impossible. In R2 minus the origin, there is no homotopy between these two circles. Okay, but we won't be able to prove it now. We will have to use more sophisticated tools. Okay. Now we have homotopies. We can define trivial maps. So we say in topology that a map is trivial if it is homotopic to a constant map. This is the point of view we adopt. For us, all the constant maps and the maps that are homotopic to a constant map are trivial. They are zero. And in some cases, there only exist trivial maps. For instance, all the maps that goes onto Rn are trivial. They can be, they are homotopic to a constant map. So if you want to study the theory of homotopy of maps that goes into Rn, this is not an interesting theory because everything is trivial. So let us prove this result. I take a continuous map, F, from any topological space X to Rn, and I want to prove that F is homotopic to a constant map. To do so, I have to build a homotopy and consider this one. To a point in X time the interval 0, 1 should be written here xt to a point xt. I assign t times f of x. So as you can see, if I take t equals to 0, I have 0 times f of x. This is 0. F dot 0 is a constant map equal to 0. Now, if I take t equals to 1, I have 1 times f of x. This is f of x. So f dot 1 is equal to f. Hence, this map big F is a homotopy between my first map F and a constant map. So every function that goes into Rn is trivial. And this is the case also in the other direction. You can show that any map with domain Rn is trivial. Any map with domain, the Euclidean space, is homotopic to a constant map. And this will be an exercise for you. Okay. So in conclusion, when we talk about homotopy maps, we have to make sure that our domain or codomain are not the Euclidean spaces, or this is not very interesting. For instance, as we've seen before, if my space X is a circle and the codomain is the plane without a point, these two spaces are not Euclidean spaces. And so this is interesting to understand homotopies between them. And Igor asks, in this slide here, it is not X which is mapped to T times f of X, it is xt, exactly. All right, if you don't have questions, we can talk about homotopy equivalence between topological spaces. Let's go. So we have this big definition, so follow me. I consider now two topological spaces, X and Y, and I will define a homotopy equivalence between these two topological spaces as a pair of maps. The homotopic equivalence is the data of two maps, F from X to Y and G from Y to X, such that the composition GF, so GF, this is a map between X and X. You start with X, you apply F, you are in Y, and then you apply G, you are again in X. I want that this composition to be homotopic to the identity between X and X, okay? And also, the other composition, FG, FG, so I am in Y, I follow G and then I follow F, so this is a map from Y to Y. I want this map to be homotopic to the identity from Y to Y. All right, so this is the definition of a homotopy equivalence. And if I have such a homotopy equivalence between the spaces X and Y, then I will say that X and Y are homotopy equivalent. So all this definition is drawn here. You want this composition to be homotopy equivalent to the identity, and this other composition to be equivalent to the identity. So this is a very nice definition, though it is quite hard to use in practice. So I want to give you a tool now to prove that spaces are homotopy equivalent without using this complicated definition. And this tool, this trick, is called deformation retractions. This works when one of the sets, X and Y, is a subset of the other. So consider a topological space, X, and a subset, Y. You endow Y with a subspace topology. So for instance, in this example, I took X to be the annulus, this band, this strip, and Y is the circle inside the strip, inside the annulus. I define a retraction as a continuous map that goes from X to Y, and such that for every point of Y, the image of Y by the retraction is Y. So a retraction is a map from the whole space onto the subspace, the subset, that stabilizes the subsets. The map is a constant, is the identity on the subset. I give you an example of a retraction here. To every point of the annulus, map it to its projection on the circle. Okay. So basically, you have your annulus, and you retract each part of it. You contract to the inner circle. Okay. And now, I define a deformation retraction as a homotopy between the identity map of X and any retraction of X to Y. All right, so for instance, here I define this retraction where you just project points on the inner circle. A deformation retraction will be a homotopy between the identity on the annulus and the retraction. And why is it so nice? Because if I have a deformation retraction, then my two spaces are homotopic equivalent. If I can prove that this retraction I define is a deformation retraction, then X and Y are homotopic equivalent. Let's prove that. So Lucas says that in the chat, the identity map and R do not share the same codomain. That's right. Because when I say a retraction R from X to Y, this is to make clear that the image of the retraction is Y, but actually the retraction is a map from X to X, because Y is a subset of X. If I want it to be very formal, I would say something like from X to X here. From X to X. Yeah, that's right. I should write that only to make things clear that I wrote Y.
I have a question.
Yeah.
The R map will be defining I instead of X.
Can you repeat, please?
The R map, the retraction map, should be defined in I instead of X, isn't it?
No. The domain, the first space, the domain of the map must be X, must be the whole space. And the codomain, the image, must be also X, but as oh yeah, As it is written, this is false. I should say a retraction is a continuous map R from X to X, such that we have this condition plus, can I write, plus for all X, oh, this is difficult, in big X, we have R of X is in Y. Does it answer your question?
Yes. So basically, the functions say that in the I, we have an identity, but the rest can be any function, any continuous function.
Exactly.
Is that right? Oh,
that's it.
okay. Thank you.
So yeah, I wrote at the beginning R from X to Y so that I doesn't have to have this other condition. Nice. Thanks for your questions. So now I would like to prove this result. If I have a deformation retraction, then the spaces X and Y are homotopic equivalent. So this is actually very simple. I take a deformation retraction, that is a map R from X to Y, and a homotopy, we will use that later. And I also consider the inclusion map from Y to X. So whenever you have a set and a subset of it, there is an inclusion map. The inclusion map just being the map that maps any point of the subset to itself in the larger set. This is always denoted I, like that in topology. And I will prove here that the pair Ri is a homotopy equivalence. And so we will prove that the spaces X and Y are homotopic equivalent. So first condition. So remember the definition was here. I have to make sure that both compositions are homotopic to the identity. The first composition is I R. This is a map from X to X. And actually, yeah, so YR is equal to R because R has its image into Y and I is the inclusion. So R is R. And by definition of a deformation retraction, I know that R is homotopic to the identity between X and X. This is the definition. So I know that this composition is homotopic to the identity. So we're very good. The other composition is Ri. But oh, there is a mistake. Here, I say, let us prove that Ri is homotopic to the identity. This is obvious because Ri, and not IR, Ri is the identity on Y. Let me correct that. I R. because if you take a point in Y, its image by R is itself, by definition of a retraction, and then its image by I, the inclusion, is also itself, by definition of the inclusion. So this map is equal to the identity. And a map is always homotopic to itself. The identity is homotopic to the identity. So we prove that the composition.
Rafael.
Yeah.
I missed the definition of the inclusion map. It's just the inverse function of the retraction.
The inclusion map. Let me. Yeah, I will write something here. So we have Y subset X. Y is included in X. And I can define the inclusion map I from Y to X.
Sorry, Rafael, I think that the text isn't showing for us.
Oh, all right. So I will write in the chat. Oh. So I have Y subset X, and I will define a map, the inclusion map from Y to X as follows. I of little y is equal to y. Yeah, the drawing does not work. I wrote in the chat. Can you see what I wrote in the chat? Oh, no, I wrote to people.
Oh, no.
Oh, I wrote to people.
We can't see.
Yeah, I wrote to people in the waiting room. Wow. Okay, I will again. Y is a subset of X. And I will define the inclusion map from Y to X. And here is the definition. Map a point of Y into itself, seen in X. So you may be confused because it's actually very simple, but sometimes the most simple things are quite awkward to grasp.
Okay, so in this case, you're not actually mapping every point of Y to X. You're just mapping Y to itself.
You map Y to itself seen in X, which is basically the same.
Okay. Thanks.
Okay. So we were here. Okay. And now you understand that. So yeah, so let me correct that again. Can you see when I draw here?
Yes.
Yes, nice. So you agree that Ri, the composition Ri, is the identity. I don't understand what Lucas is. Okay, nice. So now let's use this tool I just gave to you. We can easily show that spaces are homotopy equivalent just by defining a retraction and showing that this retraction comes from a deformation retraction. Very important example. I show here that Rn, the Euclidean space of dimension n, is equivalent, homotopy equivalent to 0, to the point 0. Let's take a very simple retraction. From Rn to Rn, 0 here represents the origin of Rn, the vector 0, 0, 0, 0, n times. So the retraction is simply you take your space and you crunch everything into the origin. I will define a homotopy between this and the identity. Very simple. Large F maps. So again, a mistake here. Sorry. This should be a point xt. I map a point xt of Rn times the interval to 1 minus t times x. If you take t equals to 0, you have x, 1 times x. So f dot 0 is the identity. And if I take t equals to 1, I have 1 minus 1 times x. This is 0. This is the retraction R we just defined. So this retraction comes from the deformation retraction, and we can use the previous proposition to conclude that Rn and the origin are homotopic. So this is very different from homomorphisms that we have seen yesterday. Another example, a bit more complicated, but also very important. I want to prove here that the Euclidean space without the origin, Rn minus the origin, is homotopy equivalent to the sphere in Rn. Okay. In other words, if I take the Euclidean plane and I remove a point, then this is the same as the sphere, homotopy wise. And this is my retraction. Take any point in the Euclidean space and map it to itself divided by its norm. Okay. This is actually an element of the sphere, because the sphere is defined as the set of points with norm equal to 1. And you can see that this element here has norm equal to 1. So look at this drawing here. To any point, up, I map it, I retract it to the sphere, the circle here. I have my Euclidean space, and I retract angular-wise the points. Let us prove that this is homotopic to the identity. It is thanks to this deformation retraction. And again, to be very clear, I will write xt.
Professor, if we include the 0, is not homotopic anymore?
No, it is not. And as you can see in this example, you cannot define this retraction at the point 0. You cannot divide 0 by its norm. 0 over 0 does not make sense. And there is no way of extending this map, the retraction, to the whole Euclidean space.
Yes, this map, but do we have I don't know, a theorem saying that the map is always unique?
No. I'm just saying that this map could not be extended, but you can also show that Rn is not homotopic to the sphere. So no homotopies, no retraction exists, no deformation retraction. And we will prove that in a few slides, but we will need some invariants to prove that.
Seems pretty difficult.
No, thank you for interrupting. Okay. All right, so I gave you a few examples of deformation retractions. And now we will do the same thing as yesterday. We will try to understand topological spaces from a homotopy equivalence point of view. So let me write x equal to y, equal with two waves. I don't know how you call this symbol. I write x equal to y if they are homotopy equivalent. If you can find a homotopy equivalence between them. Similar. Yeah, in LaTeX, it's approximatively. I will, yeah, similar is nice. I will use similar. Say that x is similar to y if they are homotopy equivalent. So any topological space is similar to itself, is homotopy equivalent to itself. This is really simple to prove. We also have the symmetry relation. X similar to y implies that y similar to x. So in same fashion, if you have a homotopy equivalence between x and y, fg, you also have a homotopy equivalence between y and x, gf. You just inverse the order of the maps. And at last, transitivity. If I have three spaces such that the x and y are homotopy equivalent and y and z are homotopy equivalent, then x and z are homotopy equivalent. This relation is transitive. That means that being homotopy equivalent is an equivalence relation between topological spaces. And this is really nice because now we can consider classes of homotopy equivalence. We can classify topological spaces according to this equivalence relation. For instance, the class of circles will be the class of all the topological spaces that are homotopy equivalent to a circle. The square, for instance, is homotopy equivalent to the circle. The letter Q is homotopy equivalent to the circle because you can see the circle as a subset of the letter Q, and then you can retract the tail of the letter Q onto the inner circle. So these two spaces are homotopy equivalent. The annulus is also homotopy equivalent to the circle.
Can you repeat how you can fix the little tail to make a?
Yeah. So how to prove that Q is homotopy equivalent to O? We will use this proposition. If we have a deformation retraction, then the two spaces are homotopy equivalent. So I have to find, let's say that X is the letter Q and Y is the letter O. I will do a little drawing.
Oh, I see. I see.
You see?
Yeah,
Okay.
thanks.
Okay, fine. I take the letter O. There is a tail, and I retract the tail on this point. I obtain the circle. The annulus also is a homotopy equivalent to the circle because you can retract the annulus on the circle. And of course, we are also allowed to deform continuously shapes. As for homomorphisms, this circle, this disk, is homotopic equivalent to this bended annulus. The annulus is homotopic equivalent to the bended annulus. And this annulus is also homotopic equivalent to the bended annulus with some hair on it, because you can retract the hair, these little lines, okay? And of course, there is much more topological spaces here. And this is interesting to understand what is in this class of circles. Another example, the class of points. That is the class of topological spaces that are homotopic equivalent to the point, the most simple topological space with only one element. So for instance, the line is homotopy equivalent to the point. We've seen before that the Euclidean spaces Rn are all homotopic to the point. So in this class, you have all the spaces Rn, but you also have the cross. Okay, this cross can be retracted onto its center point. You take the point and you retract the branches. The sphere, the disk also. You can retract the disk on the center point. Any line. This is another example where I take a line and I put some branches. And to show that this is a homotopy equivalent to a point, I can start by retracting the little branches, the little hair. Then I obtain a simple line, and this is equivalent to the point. And there is many more classes of homotopy equivalence. For instance, classes of spheres, of torus, of Klein bottles, just as for homomorphic spaces. Do we have a class group? What do you mean by that, Alan, in the chat? Can we describe nicely the different classes? Oh, do we have a group structure on the classes? I don't know about that. I mean, yeah, I guess you can define an interesting group structure on classes of topological spaces, because mathematicians like to put algebra everywhere. But I'm never heard about that. Okay, you're welcome. So as you may understand, what we've done here is very similar to what we've done yesterday. Yesterday, when we tried to classify topological spaces into homomorphism equivalence classes. And there is a link between homotopies and homomorphisms. Here it is. Take two topological spaces X and Y. If they are homomorphic, then they are homotopic. With symbols, I wrote yesterday this equal sign with only one wave, meaning homomorphic. Then you have the same symbol with two waves. All right? And a direct consequence of that is that if you want to prove that two spaces are homotopic equivalent, it is enough to prove that they are homomorphic. Okay? Let's prove that. I take two spaces, X and Y, and a homomorphism between them, H. I want to prove that they are homotopic equivalent. So I have to build a homotopy equivalence. And this is so simple because I will choose as a homotopy equivalence a map F equal to H and the map G equal to H minus 1. Since H is a homomorphism, F and G are continuous. Okay? But now, the composition GF, this is H minus 1 H, this is the identity on X. And the identity is homotopic to itself. Any map is homotopic to itself. In the other direction, FG is H minus 1. It's also identity between Y and Y, and this is homotopic to the identity. Conclusion, the pair of maps FG is a homotopy equivalence between X and Y. And we deduce that X and Y are homotopy equivalent. Example, the letter L and the letter Z are homomorphic. You can define a simple homomorphism between them, something like that. And we deduce, according to this proposition, that they are homotopy equivalent. So let's start again. Share my screen. Did you follow my explanation of proving that L and Z are homotopy equivalent because they are homomorphic? And I have a question of Guilherme. Can you give us, in the chat, can you give us an example of two topological spaces that are homomorphic, no, that are homotopic equivalent, but not homomorphic? Or does the converse also hold? And Guilherme's answer to your question is the next slide. Now, some spaces are homotopy equivalent, but not homomorphic. And a simple example is the space Rn and the point 0. We've seen yesterday that they are not homomorphic.
Rafael,
Yeah,
can I ask a question?
of course.
So I can see a motivation behind homomorphism. I mean, if spaces are homomorphic, you can think, for example, they can behave locally like an Euclidean space. if they're homomorphic to an equivalent space. But what is the motivation behind homotopic? Like, is there any intuition behind it? Like, if spaces are homotopic, what kind of structure do we get that is interesting?
Yeah. For instance, I feel that this is very natural to say that the circle, and the thickening of the circle, the annulus, are the same thing. Or another answer would be that homeomorphism is a very strict relation. And actually, these two relations have different meanings. So it depends on what you want to do with topology. For instance, in topological data analysis, most of the time, we want to understand the homotopy class of our data. If our data is a circle or a circle with some branches, we will say that this is the same. We will not make difference between a circle and a circle with branches. But in some experiments, you want to tell the difference between such spaces. So you would rather use the homomorphism perspective. So really, it depends on what you want to do. And another answer will be, as we will see next week, there are topological concepts, topological notions that are better defined at the homotopic level. So it is mathematically more easily to deal with homotopic spaces than homomorphic spaces. But really, you have the choice of what you want to use. Does that answer your question?
Yeah, thank you.
Okay. Now I have a little exercise for you. Please take 5 minutes to tell me. So I take the first 6 letters of the alphabet, A, B, C, D, E, F. I want you to classify them into homotopy equivalence classes. I want to tell me which one of them are homotopy equivalent. And then, once you've done that, I want you to classify them into homomorphism equivalence classes. So please take 5 minutes to do that. You can write your answers in the chat when you're done. 2 minutes more and we correct. I see a lot of very good answers in the chat. All right. Almost everyone is right in the chat. Homotopy equivalence classes, we have 3 of them. We have actually 3 types of topological spaces: the point, the circle, and the double circle, the bouquet of 2 circles. Let me start with A. A is a circle because you can retract the 2 branches to obtain a triangle, and this is homotopic to a circle. This is even homomorphic to a circle. And D also is homotopy equivalent to a circle because it is even homomorphic to a circle. B, this is different. You can find a homotopy equivalence between it and the union, the gluing of 2 circles. And oh, there is a mistake. D is not a point. Annotate. This is not D, this is... Okay, all right. This is what we have. C, E, and F are points because you can choose any point in them and retract the whole space onto this point. All right. And what do you say about homomorphism?
Sorry, Rafael, could you repeat the argument for the point?
Yeah. To prove that the letter C, E, and F are points, are homotopy equivalent to points, we will find a deformation retraction from the letter to the point. For instance, take C, the letter C, and pick any point in C. You can retract the letter C by the retraction, the trivial retraction that maps each point to the points you choose. And this is a deformation retraction because this is a continuous deformation. So you take the letter C and you retract the branches into 1 point. As I explained that, you may think that this is not really mathematical, but the thing in topology is that most of the time we do stuff like that doesn't look very mathematical, but you can always write down the actual mathematics behind it.
I don't know if this is a silly question, but couldn't you retract the circle to become a point also?
No, because this is a very important question. If I want to retract the circle on the point, so I have to define a retraction. So let's pick a point. You know, there is a problem at the other side of the circle, because I would have to cut the circle to, at some point, points will have to go in a different direction. So the retraction will not be a continuous map. You will have to cut your circle to retract it on a point.
Okay, thanks.
All right. Let's see how homomorphism classes look like. And there is again a mistake. This is homomorphism. We have 5 classes. The only 2 spaces between A, B, C, D, E, F that are homomorphic are the letter E and F. Because take the letter E and move the first branch here, you obtain a F. You can define a simple homomorphism between E and F, but it cannot be done with the other letters. Let me read the chat. That joke with the cup and the donut is a homotopy or homomorphism. This is a homomorphism, but be careful, because when we say that a mug is the same thing as a donut, we do not consider the usual torus, the usual donut, because the usual torus is empty. We only consider its boundary. But in the example where a mug is a torus, the torus is filled. I call it the filled torus. So the filled torus is the same thing as the mug, because basically you can deform the torus to obtain a mug. So this is a homomorphism. This is stronger than homotopic. Okay. So let's get to the next, to the last section. I want to study with you what invariance we can define on the equivalence relation of homotopic equivalence spaces. So let me recall you that yesterday we studied 2 invariants, 2 quantities, the number of connected components and the dimension. I want to know how they behave at the homotopic equivalent level. And good news for us, the number of connected components is an invariant of homotopic equivalence. In other words, if I have 2 homotopy equivalent topological spaces, then they share the same number of connected components. And let's not read the proof today. It's a bit more difficult than the other one we've seen. If you're interested in the proof, have a look at the notes. What I want to emphasize is the same thing as yesterday. Thanks to this invariant, we can easily show that spaces are not homotopy equivalent. You just have to show that they do not have the same number of connected components. And I give here a simple example. Take n and m integers, different integers, and consider the subspaces of R that consist in the first n integers for the first set and the first m integers for the second set, endow them with the subspace topology. This one has n connected components because you have n isolated points, and this other one have m connected components. They do not have the same number of connected components, hence they are not homotopy equivalent. Lucas asks, the converse is true. What converse? Do you mean that if they share the same number of connected components, then they are homotopy equivalent? Yeah, no. Unfortunately, this is not true. Number of connected components is not an invariant that totally describes the topological spaces up to homotopy equivalence. And for instance, take a point and the circle. We've seen that they are not homotopy equivalent, though they have the same number of connected components. Thank you. And Guilherme asks, 8 and 0, 0 in R2 are not homotopic. Yeah, because 0, 0, this has two connected components, and 8, only one connected component. So indeed, they are not homotopic, even though they have the same number of holes. And I'm glad that you see this, because when we will talk about homology next week, number of holes will be very important for us. All right, last slide of the lesson, dimension. Is dimension an invariant of homotopy equivalence? Unfortunately, it is not. You have topological spaces that are homotopy equivalent, but does not have the same dimension. If you take a class of homotopy equivalence, so a set of homotopy equivalent topological spaces, and this is it. I introduced today the homotopy equivalence between topological space. We've seen that this is a weaker notion than homomorphism. So depending on the cases of the problem, we will adopt a homomorphism equivalent perspective or a homotopy equivalent perspective. And between the two invariants that we've seen yesterday, only one is an invariant of homotopy equivalence. And so you have two exercises for tomorrow. And thank you very much, everyone.